Example 9.2, which would require a greater force accelerating a 2 kg mass at a 5 meter per second square or a 4 kg mass at a 2 meter per second square. Okay, from the equation 9.4, okay, which we have already studied, that F is equal to ma. Okay, in which we have studied that F is equal to ma. Force is equal to what? Okay, mass into acceleration. Okay, the product of mass and acceleration is said to be a force. Okay, so here you can see that mass m1 is given 2 kg, and same way for that acceleration is 5 meter per second square. Okay, there is a present of 5 meter per second square. So if we find out the mass or an acceleration which are given, okay, through which we will find that a force. Okay, F1 will be 2 kg into 5 meter per second square. So it will be 10 Newton because 5 2s are 10. Okay, same way if we find for the second case, okay, in the second case we have given that m2 as a 4 kg and a2 which is acceleration is of 2 meter per second square. Okay, finding that we will find that for first case it will be 10 Newton force and for the second one it will be 8 Newton. Okay, through this we can find that here the F1 is greater than F2. So from this we can find that force F1 will be greater as compared to F2. So thus acceleration of a 2 kg mass at a 5 meter per second square would require greater force. Okay, as compared to second one. Same way, example 9.3, a motor car is moving. Same way, a motor car is moving with a velocity of 108 km per hour and it takes 4 seconds to stop after the brake are applied. Calculate the force exerted by the brake on the motor car if its mass along with the passenger is 1000 kg. Okay, if it is 1000 kg, then we have to find the force exerted by the brake on the motor car. Okay, now here we can see that initial velocity of a motor car is 108 km per hour. Okay, if we convert it into a meter and per second, so it will be meter per second. So we know it very well that 1 kilometer is 1000 meter, and same way 1 hour is equal to 3600 seconds. So total will be 30 meter per second. Okay, and final velocity if the motor car is stopping or if it is stopped, then at that time its velocity will be 0. So here our final velocity will be 0. Okay, so the total mass of a motor car along with the passenger, here mass is also given, how much? 1000 kg, and the time which is already given for second. We have the magnitude of the force applied by the brake is F is equal to m v minus u upon t. Okay, which is ma only, where a is replaced by or substituted by v minus u upon t, which is final velocity minus initial velocity upon time. Okay, so here our m is 1000 kg, final velocity is 0, initial velocity is 30, okay, and our time is 4 seconds. So if we convert it into a force, then it will be minus 7500, which will be 7500 kg meter per second square. The negative sign here, okay, the negative sign tell us that a force exerted by the brake is opposite to the direction of the motion of a motor car. Okay, which is totally opposite to the motion of a motor car. That's why here force is negative. Example 9.4, a force of a 5 Newton gives a mass m1 and the acceleration of a 10 meter per second square, and a mass m2 and acceleration of 20 meter per second square, what acceleration would it give if both the mass were tied together? Okay, if we are tying both the mass together, at that time how much acceleration will be given? So here we have a m1. How m1? Because we know it very well. F is equal to ma. Okay, F is equal to ma. If we prepare a subject of equation or subject of formula of a m, okay, we have taken mass as a subject of equation or subject of formula, then it will be m1 is equal to F upon a1. Okay, so for that acceleration which we have given 10 meter per second square in a question only, and same way a2 is 20 meter per second and F is 5 Newton. Thus m1 is equal to 5 Newton upon 10 meter per second square, so it will be 0.50 kg. Same way if we find m2, it will be 5 upon 20, because in that acceleration is changing, so 0.25. Okay, so here both the mass are tied together, it will be 0.75, and then we have a formula, total force which is 5 Newton, mass which is 0.75. Okay, so F upon m. So our A acceleration will be 6.67. So we will need to give acceleration of 6.67 if we tie both the mass. The velocity time graph of a ball of a mass 20 gram moving along a straight line on a long table is given in figure. Okay, how much force does the table exerted on the ball to bring it to a rest? Okay, the initial velocity of the ball is 20 centimeter per second square. Okay, if we take, due to the friction force, the velocity of a ball decreases down to 0 in 10 seconds. How much second? Okay, it will convert it into a 10 second. Thus the initial velocity is 20 centimeter per second, and here our final velocity is 0 centimeter per second square, because it is stopping, that's why, and the time is 10 seconds. So our final, the ball will be at a rest. So since the velocity time graph is the straight line, create that the ball move with the constant acceleration. The acceleration A is v minus u upon t. Okay, from the graph we can find out that the acceleration is constant. Okay, so A is equal to v minus u, which we say it as a final velocity minus initial velocity upon time taken. So our final velocity, which we have already known, that 0, and initial, which is 20 centimeter per second square, divide by 10, so it will be minus 2 centimeter per second square. Now if we convert centimeter into meter, it will be 0.02 minus 0.02 meter per second square. Yeah. The force exerted on the ball, now we have find mass, which is 20 upon 1000 into minus 0.02 meter per second square. Okay, so it will be 0.00004 Newton, or we say it as a 4 into 10 raised to minus 4 minus 4 into 10 raised to minus 4. So the negative sign implies that the force exerted the table is opposite direction of the motion of a ball. Okay, now our topic, third law of motion. Third law of motion. Okay, now we have already studied two law of motion. The first two law of motion tell us how an applied force changes the motion and provide us with a method of determining the force. Okay, how we can find out the force by different type of situation. The third law of motion states that when a one object, okay, the statement of third law of motion, when a one object exerts a force on another object, the second object instantly exerts a force back on the first. Okay, third law states that when we are exerting a force, okay, we are giving a force to a one object, and that force will be exerted by the another object. okay, which is beside that first object, and due to which, okay, second object will give a instant force to the first one. Okay, so here we can see that if we are applying a force to a first one, then it will be a force exerted to a second one, and that second one will give a force back to the first one. Okay, this is the third law of motion, okay, which we say it as every action has its equal and opposite reaction. Okay, if we are giving an action, then there will be a something reaction also. Okay, some reaction will be there if we are exerting a action. These two forces are always equal in magnitude but opposite in direction. Obvious, if we are giving a force to the first one, okay, that direction will be towards the second one. In same way, second one is also giving a force to the first one, but the direction will be opposite. Okay, if the direction of a first one is right, then second one will be on a left one, because it is giving a force towards the first one. Okay, so the both of them will have a different or a opposite direction. These force act on the different object and never on the same object. Okay, that force will be exerted on the second object, or it can never be exerted on the same object. In the game of the football, if we talk about the game of a football, sometimes we, while looking at a football and trying to kick it with the greater force, okay, what will be seen? Collide with the player of the opposite team, and both feel hurt because each apply a force to the other. Okay, why? Because if a football is trying to kick it with a force, okay, then collide with the player of the opposite team. Okay, if the opposite team player is also colliding, okay, then what will be seen? Both of them will be hurt because each apply force to the other. Okay, they both of are giving a force, okay, but both of them have a force opposite to each other. That's why both of them will be injured, and not just on a force. The two opposing force, okay, are also known as action and reaction force. Okay, the two force which are exerting on an object. Okay, one is said to be a action and another one is said to be a reaction. Okay, so in third law of motion, we have studied that on an object force will be exerted, and the two type of force will be there. One is action force and another will be reaction force. So present of two forces, action force and reaction force. Let us consider a two spring balance connected together. Okay. Here you can see, okay, action and reaction force are equal and opposite. Okay, we are talking about this. Okay, the fixed end of a balance B is attached with the rigid support like a wall. Okay, B is attached with the rigid support like a wall. Then what will be seen? When a force is applied through the free end of a spring balance A, we are exerting a force to a balance A. Where we are spring balance A, we are exerting a force on a spring balance A. It is observed that both the spring balance show the same reading on their scale. On their scale, they will show same reading. It means that a force exerted by the spring A on the balance B is equal but opposite in the direction. Okay. So if we are exerting a force in a spring balance A, okay, that much amount of force is exerting on B also. You can see it in a graph, okay, graph or in a figure, okay, which we are seeing that if we are exerting a force A, then that much amount of force is only applied to the spring balance B. Balance B on the balance A. The force which balance A exert on the B is said to be an action, and the force balance B on the balance A is called the reaction. Okay, if we talk, then we are exerting a force. Okay, here you can see that. Okay, A is exerting a force. Okay, that will be said to be an action. In same way, if B is exerting a force on A, that will be said to be a reaction. This gives us an alternative statement of a third law of motion, that is to every action, okay, which are giving a statement of that only third law of motion. That every action there is an equal and opposite reaction. If we are giving any action, okay, that much amount and that much amount of magnitude of reaction will be seen. Okay, so from this we can say that every action has its equal and opposite reaction. Okay, from this we can say that every action has its equal and opposite reaction. Same way, however, it must be remembered that the action and reaction always act on the two different objects. Okay, the action and reaction will be on a two different objects. Okay, that much will be exerted on each other. Suppose you are standing at a rest. Okay, now we will study some examples. Suppose you are standing at a rest and intend to start walking on the road. You must accelerate, and this required a force on the accordance with the second law of motion. Okay, if we are first we was standing and then we have started walking, what will be seen that some much amount of acceleration will be required for giving a force towards the rod. Okay, which is this force? Okay, which is this force? Is it the muscular effort you exert on the road? Is it in the direction we intend to move? No. You push the rod. Okay, here we are what doing? We are pushing the rod below backward. Okay, that's why force will be exerted, and due to which, okay, a body will accelerate or move towards forward. Okay, it will move towards forward, and the rod exert an equal and opposite reaction force on your feet. Okay, we are what giving a force, okay, below backward. Okay, due to which rod will give its reaction, okay, to the feet. It will give a reaction to the feet, and due to which a person can able to move forward. Okay, it will able to move forward. It is important to note that even though the action and reaction force are always equal in magnitude, this force may not produce acceleration of the equal magnitude. Okay, they will not produce equal magnitude acceleration. This is because each force act on a different object. Here you can see that each the force, okay, both the force are exerting on a different object that may have a different mass, and both of them have a different mass, and due to which the equal amount of magnitude cannot be seen, okay, of an acceleration. When a gun is fired, okay, now we will take one example. When a gun is fired, it exerts a force which will be in a forward, okay, on the bullet. Okay, on the bullet it will be a force towards the forward. Same way, a bullet exerts an equal and opposite reaction force on the gun. Okay, when we are firing a bullet from the gun, okay, what will be seen? A bullet will go forward. Okay, its direction will be forward, but we can see that some jerk will be filled on the hand. Okay, whenever we are firing a gun, okay, opposite force will be exerted on the gun, and due to which it will move backward. Gun will move backward when we are firing a bullet. This result in the recoil of a gun, and since the gun has much greater mass than the bullet, the acceleration of a gun is much less than the acceleration of a bullet. If we compare, okay, gun have a larger mass as compared to a single bullet. Okay, due to which a gun will accelerate more as compared to a bullet. The third law of motion can also be illustrated with the shaded jump out of a rowing boat. As the shaded jump forward, the force on the boat move it backward. Okay, whenever a Sardar is moving forward, what will be seen? Okay, he is giving a force towards forward, but due to which a boat will go to backward. Okay, boat will go towards backward. Okay, so from this you can see that the force is exerting towards the forward, while the reaction is done of a boat towards the backward. Okay, so from this we can say that Sardar is giving a force towards the forward, which we say it as action, while a boat is going towards the backward. Okay, which we say it as a reaction. So from this we can say that every action has its equal and opposite reaction. Okay, so in gun also we are saying that when we are firing a bullet, at that time bullet will go towards forward, but the gun will give a force towards the backward. So this way the action and reaction can be explained. Now place two children on one card, one on another card. Okay, what will be seen? The second law of motion can be seen. What we are seeing? Second law of motion of a scene. As this arrangement would show different acceleration for the same force. The cards shown in this activity can be constructed by using 12 mm or 18 mm thick plywood. Plywood board of about 50 cm or 100 cm with the two pair of hard ball bearing wheels, okay, which we say it as a skateboard. Skat wheels are good to use. Skateboard are not as effective because it is difficult to maintain straight line motion. Okay.
While studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet. And the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun. A perfect example of Newton's third law. But hold on. If the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration. Or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor?